Hi, everyone. Welcome back to the Zoom talk session. I hope everybody enjoyed the poster session as well as the couple of talks we had in the morning. So continuing on the amazing lineup of talks, I'm very happy to introduce my colleague, Virginia Smith. She is an assistant professor in the machine learning department at Carnegie Mellon University. If you have worked or read papers on federated learning, you have probably heard of her name. Her research interests span machine learning, optimization, distributed systems. And before joining CMU, she was a postdoc at Stanford. And before that, she received her PhD from UC Berkeley and did her undergrad at University of Virginia. So I'm very happy to introduce her. Virginia, you can start whenever you're ready.
Awesome. Thanks, Gary. Yeah, thanks for giving me the opportunity to speak. I'm really happy to be here today and, reflecting on challenges in communication efficient distributed optimization. As Gary mentioned, I've been doing a lot of work in federated learning. And so my mind really went there. And one of the things I wanted to highlight today in my talk is something that's unique about the federated setting, which is this additional challenge beyond communication efficiency of heterogeneity. So I'll talk about the issue of heterogeneity today from multiple different angles, both in thinking about some new challenges that this introduces to the machine learning pipeline, but also potentially some opportunities this might afford us when performing distributed machine learning. So let me start by just giving some context for what federated learning is and why we might care about this problem. So overall, the goal of federated learning is simply to perform training at the edge. So we want to train some machine learning model at the edge. There are many reasons we might prefer this to something like a traditional cloud-based training scheme where you send potentially all of the raw data from a network of devices to some central location. So this can be useful to more quickly incorporate new data that you see to help reduce strain on the network. And then beyond these, computational or efficiency reasons, there can also be some privacy benefits for keeping the raw data local on the devices in the network. Okay, so in terms of thinking about the federated setup, just to ground this with a specific kind of objective, the objective that we commonly think of when training these federated learning models would be something like an empirical risk minimization objective. So you want to find some optimal model that minimizes a sum of losses over your n devices, where f sub k here represents the loss on one of the devices k. And the way that training proceeds would be, for example, that you have some central server that's aggregating all of the updates from the devices. And at each round, this server sends the current model iterate to a subset of the devices. Those devices then perform some local training and send their model updates back to the central server to be aggregated and used for the next iteration of your distributed optimization method. Okay, so what I've just described sounds a lot like distributed optimization and distributed training in other distributed settings, like, for example, the data center setting. But there are a few challenges that make federated learning pretty unique. So one is that because we're thinking about performing this over a potentially massive network of devices, think, for example, of a network of mobile phones. Communication here is always a known bottleneck in distributed settings, but in federated learning, it can become quite expensive. It can become quite a large bottleneck. So you might have massive networks. The networks themselves can also be quite slow. And you can have issues with communication that maybe aren't present in a data center environment. You can have practical issues like someone turning off their phone or having issues with battery power, things like that make communication particularly difficult and expensive. Okay, beyond this, as I mentioned, there can be privacy reasons that motivate federated learning to begin with. And indeed, there are additional privacy concerns that we have to think about when performing this distributed training. So even though we could potentially get some privacy benefits from keeping the raw data local to these devices and performing training in a distributed fashion, there are also privacy concerns with sending these model updates across the network. And so you have to consider these specific user privacy constraints when developing distributed training procedures for federated learning. Okay, another big way that this setting differs from something like distributed computing in a data center is that because you assume that these devices are generating some data, so let's take, for example, a network of mobile phones. It could be that you're trying to learn some language model over a set of phones where you're looking at some text message data. Right, and it could be that some people text more frequently than others, or some people text in a different way or a different language than others. And for this reason, the data can be extremely heterogeneous across the network. So it can be unbalanced and non-identically distributed. You might have data on some devices that looks different from data on other devices. And this will kind of be a major focus of the talk today, is thinking about various ways that this might impact the machine learning pipeline in federated settings. Okay, and I wanted to note lastly that heterogeneity comes not only from the data potentially, but also from the underlying hardware and system setting. So for example, you might have some devices with, you could have a newer phone and someone has an older phone, or someone has, more battery power or less battery power or better connectivity. And all of these kind of practical systems constraints can affect how capable each of the devices are in terms of participating in the training procedure at each round. So there can be heterogeneity not only in terms of the data, but also in terms of the underlying hardware. Okay, so while all of these are critical concerns that really differentiate federated learning, especially when taken in unison from other distributed training regimes, today I'll be focusing really on the issue of heterogeneity. I wanted to note here, if you're curious and interested in learning more about some of these challenges and other techniques that have been developed for federated learning, I wanted to just point out two resources. One is a white paper that we wrote last year on some of the challenges and future directions in federated learning. And another is a recent NeurIPS tutorial on federated learning. Okay, but again, today I'll be focusing specifically on these issues of heterogeneity and thinking about various ways that this particular challenge can affect the machine learning pipeline for federated learning. All right, so let's dive a little bit deeper into this question. And by the way, as I'm going through, if you have any questions, please feel free to stop me. You can just unmute yourself or put a question in the chat window, and I'll try to make sure that I address it. But to dive a little bit deeper into this question, how could heterogeneity possibly affect the machine learning pipeline in federated settings? One of the maybe most obvious things that might come to mind is thinking about how heterogeneity affects this optimization method that we're trying to perform in a distributed fashion, right? So how does this particular challenge of heterogeneity affect federated optimization methods? But it turns out that heterogeneity doesn't just stop with this training procedure. In the sense that heterogeneity can also affect the model that you've trained in terms of how it performs on the overall task across all of your devices. And it may affect things like, for example, how equitable that model is. So how does that model perform, particularly when you have a network that's very diverse? So if you have a federated network where the devices are generating data potentially that looks very different from one device to another, it can be difficult to learn a single model that performs equally well across all of those devices. And so trying to enable this kind of fair or equalized performance can be a nice thing to do from a quality of service perspective. Okay, even more fundamentally, one of the major questions here is, in the last slide I showed you, we assumed that we had some fixed optimization objective that we were trying to solve with some distributed optimization method. I think another critical question, though, is what should that objective actually be? So, for example, should we be learning just one model across this potentially diverse network, or should we potentially be thinking about how to learn models that are personalized to the heterogeneous data that's being generated across these devices? Okay, so these are a few questions that I wanted to throw out to kind of start the discussion on how heterogeneity may affect federated learning. And I'll talk about a little bit of our work in the context of these three problems. So specifically looking about how heterogeneity may affect federated optimization methods, how it may affect the issue of fairness in federated settings, and how it might affect this kind of underlying goal of how should we actually be modeling the data in a federated network. Okay, and I wanted to note here that the work I'll be talking about today, I'll be talking about several works, and this is joint work with a lot of really fantastic students and collaborators. So I'll try to point out the names of those folks when I talk about some of the specific work here. Okay, so let's start here talking a little bit about optimization. So how can heterogeneity, both from a systems and a statistical point of view, affect a distributed optimization method that you're running in a federated network? Okay, and I wanted to start here and relate this back to kind of one of the overarching goals of the workshop, which is thinking about communication efficiency, right? So one of the most popular methods for federated learning is a method called federated averaging. And what federated averaging does at a high level, this looks a lot like the slide that you saw previously. So basically, we assume we have some aggregator. So this, one node, for example, could be a central server. And at each communication round, this server sends the current model to a subset of the devices. Those devices then perform some local training. Specifically, you could be performing epochs of mini-batch SGD locally. And then you send your model updates back to the central server. Okay, and specifically, when we send them back in federated averaging, these updates are averaged. Okay, so why has this become such a popular method for federated learning? One of the reasons is that, and this has been documented in other distributed settings as well, but one of the reasons that this has become very popular is that this local training procedure, where you're actually running some steps of, say, mini-batch SGD locally on each of the devices, can significantly reduce the total number of communication rounds needed for convergence. So this is a particularly useful technique when we care about something like communication efficiency. Okay, so high level, this is a very popular method. It's a simple method, which is great. It works remarkably well in practice. It really helps to reduce this communication bottleneck. But one issue specific to to this problem of heterogeneity is that the convergence can really be hurt when you're running this method in heterogeneous settings. Okay, and what specifically do I mean by that? So this is just one example looking at the performance of federated averaging on this popular Shakespeare benchmark. And what I'm showing in this plot, this will be similar to many of the plots that you'll see today, is the number of communication rounds on the x-axis and the training loss on the y-axis. Okay, so we want to ideally reduce the training loss very quickly in terms of the number of communication rounds. And what you see for this particular benchmark is that if you run this federated averaging method, and you're running this over this benchmark Shakespeare, which inherently has some heterogeneity in terms of the way that the data is generated across the devices in this benchmark. If you run federated averaging and you have a small amount of local updates, say you just do a little bit of local training, you use one epoch locally of mini-batch SGD, for example, you can roughly converge to a fairly low training loss in a reasonable number of communication rounds. Okay. Now, ideally, we would like to reduce communication even further, potentially, by increasing the amount of local training that we're doing to reduce the total number of communication rounds. Right? But if you do that, the issue that you start to see with something like federated averaging, and we're showing some kind of more extreme examples here, but if you end up doing a lot of local training, what you can see is that for these heterogeneous data sets where the data might not be IID distributed across the devices, you can get behavior that looks like this. So as you start to do more local training, you can have this issue that you're basically starting to sort of diverge to different solutions on each of those devices, and then doing something like just simply averaging those solutions doesn't result in the potentially correct training loss compared to something like running this with a smaller number of local epochs. Okay, so the punchline here is federated averaging is a great and simple method to use in practice. It's commonly used for federated learning. But when you additionally think about this issue of statistical heterogeneity, you have this problem that doing too much local work can potentially hurt the convergence behavior. Okay, and I wanted to note here that this can be a problem not just when you have statistically heterogeneous data, but also when you add in the complication of there being systems heterogeneity. So specifically what I mean by that is that if you have different devices that are capable of doing potentially different amounts of training at each round, you can have the issue that you might have some devices that are very, very slow. So you might have a significant number of devices that are stragglers. Okay, and in this setting, what's really commonly done is to just basically ignore the updates from devices that are straggling. Now, what you see, and again, this is sort of a more extreme case, but just to highlight what the issue could be, what you see is that even in a scenario where you're able to converge reasonably well, if you have a significant number of stragglers and you're just kind of ignoring the updates from those stragglers, this can really exacerbate the convergence issues that you already have present just from the statistical heterogeneity. Okay, so what can be done about this? There's actually been a ton of techniques, but I wanted to point out, one that we developed, which is called FedProx. So this is a simple way to think about tackling this issue of heterogeneity. And there's two main modifications that we make in the FedProx framework. So the first is, the intuition with federated averaging is that we want to do local updating because that reduces the number of communication rounds that we have to run this method for. But if we do too much local work, that can really hurt our convergence behavior. So intuitively, what we've done with this FedProx framework is just to take the original subproblem that you had with federated averaging and add this proximal term. And this proximal term simply is just limiting how far the update that you have to the model on that specific device deviates from the previous model iterate. So we're preventing you from doing too much work locally. And this is particularly useful when you have a very heterogeneous network. Okay, we also make another modification which specifically tackles the issue of systems heterogeneity. So because we've set up this framework in such a way that you're just kind of minimizing this local subproblem to some accuracy, we don't require you to have each of the devices running the exact same number, say, of local epochs at each round. And for this reason, we can allow you to not just drop devices that are straggling, but have devices send partial information or partial work that they've completed within a given time window. Okay, so you don't have this problem of, in a very heterogeneous network from the system's point of view, having a bunch of stragglers in the system. You can safely incorporate partial work that you're getting from the devices. So these are the two main changes that we made in this FedProx framework. And this is kind of a very general generalization of federated averaging in that, we're just defining the objective in terms of this local subproblem. You can use any sort of local solver to solve this in practice. Okay, and what kind of two nice things about this. One is that we can see that even with this simple prox term added to the objective, we can help to combat this issue of statistical and systems heterogeneity. We can also start to reason about some of the performance in theory. Oh, I think someone's drawing on the screen somehow. That's pretty neat. So at a high level, I'll just mention these convergence guarantees very briefly. But at a high level, one of the goals of the analysis here was to look at the convergence of this local updating method, federated averaging, with this additional, the modifications that we're making in FedProx. And we're able to show that in contrast to something like, vanilla federated averaging, with this modification, we can show that this optimization method can converge despite being in a setting where you have potentially non-identically distributed data, you're performing local updating, and you have partial participation from the devices in the network, which is especially important when you have issues like systems heterogeneity. Okay, specifically what we can say in terms of the convergence guarantees is that the particular rate of convergence depends on how heterogeneous your network is, right? Which makes some intuitive sense. So at a high level, we define this notion of B dissimilarity, which helps to characterize how heterogeneous your network is. So the higher this parameter B, the more non-identically distributed your data is across the network. And what we see is that we can prove that this method FedProx converges in a way that depends on this parameter. And I think that the intuitive explanation for what's going on here is that when you're running FedProx and this parameter B is large, we will also have to have this mu parameter, which in FedProx dictates how much the local update can deviate or how much local work you're doing. That mu parameter has to be larger. Right, and that overall will slow your convergence down, but you'll still be able to converge to the correct solution, and to be able to do so despite having this, this issue of heterogeneous data, and despite having potentially heterogeneity from the system side as well.
Virginia, Hi, I had a question about this equation. Does this imply that all the clients have the minima at the same point?
Yeah, that's a great question. No, it does not necessarily. So I'm not really writing out the full assumption here, but we're only assuming this that this is basically bounded and that this holds within some ball of the optimal solution. So in fact, this is kind of I think you're highlighting the exact issue with why something like federated averaging can be problematic in practice, which is that if you do a lot of local updating, you could be potentially converging to different solutions on each of the local objectives. So yeah, thanks for pointing that out.
Yeah, thank you.
So I just wanted to show these really quickly to highlight kind of two kind of benefits of the FedProx framework. One is that it gives you a little bit more of a handle on the convergence of the method. But two, we see that in practice, it can allow us to address these issues of systems and statistical heterogeneity. So for example, if you take something, and this is again an extreme case where we're looking at both issues simultaneously, there were kind of two main things that we talked about with FedProx. One is that instead of dropping devices where there are stragglers, even with just mu set to be 0, so this is basically just running federated averaging, you can get some benefits for not just dropping that information, but incorporating that information. And what FedProx can allow you to do is take that very heterogeneous information. So now there's heterogeneity not only in terms of the fact that the local data could be different, but also because each of the devices is potentially running their local method for a differing number of iterations. You can take that and you can really help to kind of stabilize the convergence behavior. All right, so two key takeaways from FedProx. One is that allowing for this partial work can help benefit convergence, and that running FedProx with this, this particular mu parameter, it gives us a handle on the convergence analysis, and it helps to improve the stability of the method. Okay. And overall, in terms of the benchmarks that we've looked at for federated learning, I wanted to just note I've shown the results here in terms of the training loss, but this also correlates with improvements in terms of the test accuracy as well. So in fact, using FedProx, we were able to see a 20% test accuracy improvement on average, and that's an absolute number. So this can result in large improvements in terms of the test accuracy as well. Okay, so I wanted to start with optimization because I think it's one of the first places that you might think about heterogeneity affecting this whole process. And in particular, there were kind of two things that we talked about in terms of heterogeneity. So heterogeneity can come from the data, but it can also come from the underlying systems. And this can lead to slower convergence, reduced stability, and potentially divergence, especially when you're using these local updating methods. And for this reason, it's really critical to analyze and evaluate federated optimization methods with these kind of practical assumptions in mind. So, thinking about the fact that the data might be non-identically distributed, or there might be partial or variable participation from the devices. Okay. Now, as I mentioned earlier, the potential challenges with heterogeneity don't stop just with this optimization method itself. So there are also questions about how the method how the model that we've learned via something like FedProx or federated averaging on this ERM style objective might perform across a network that has very heterogeneous data. Okay, and just to motivate why we might care about this, if you think about the sort of traditional empirical risk minimization objective, as I mentioned, you're typically thinking about just solving an expected set of losses, right? So you're minimizing an average set of loss objectives across your n devices. So each of these f sub 1, f sub 2 through f sub n, these would correspond to a sum of losses on a particular device. Okay, this is the kind of traditional empirical risk minimization objective. And what potential issues might you have if you try to fit this objective to data that's distributed over a very heterogeneous network of devices? Well, one issue is that because you're just minimizing the average performance, there's no real accuracy guarantee for individual devices in the network. And so what you might see is that while you perform well on average, the performance might vary widely. So you might perform well on average, but by doing quite well on some devices and very poorly on other devices. Okay, and from kind of a quality of service point of view, these are sort of cases that we want to try to prevent in practice, right? We want the model to perform well on average, but we also don't want to have situations where the model has kind of catastrophic failure on a subset of the devices. And you can see this with some of the common federated learning benchmarks. So this is one example. And what we've done here is just kind of to plot the test accuracy distribution after just training a traditional ERM objective. And you see exactly this kind of behavior in practice. So this is very expected when you have a heterogeneous data set. You might do well on average. You might have quite high test accuracy on most of the devices, but at the expense of having quite poor accuracy on a small subset of the devices. You're doing well on average, but potentially having some examples where there's sort of this catastrophic failure of the model. Okay, and so in thinking about how to formulate this objective and to try to improve beyond just kind of traditional ERM, we asked ourselves this question. So can we try to encourage a more fair or uniform distribution of the model performance, especially in networks where you have very heterogeneous devices? Okay, and thinking about formulating this problem, we took inspiration from some prior work in fairness, specifically from the wireless sensor networks community. And in particular, in this problem of fair resource allocation in sensor networks, you might be thinking about, for example, allocating something like bandwidth optimally across the network, right? And the way that we thought about kind of drawing an analogy to machine learning and to this ERM objective is that the resource that we're thinking about allocating would be these losses, right? In particular, the higher the losses on a particular device, the larger that loss is, the more your model will try to fit to that particular loss, right? If you're just minimizing the average, you're going to spend more emphasis on the losses that have a large value. Okay, so drawing this analogy and this inspiration from fair resource allocation from wireless networks, we were inspired by a particular form of fair resource allocation, which is known as alpha fairness. And using this as inspiration, we developed the following modification to ERM, which we call Q fair federated learning, inspired by alpha fairness. And it's worth noting that this kind of general framework also encompasses some prior work in fair federated learning and fairness in machine learning in general. So in particular, you can think about this as being sort of a tunable framework, where if you set Q to be 0, this recovers just the traditional ERM objective. Instead, as Q gets larger, what's happening is you're taking the losses on particular devices that might be large, and you're making them even larger. So you're amplifying devices that have high loss values. In the extreme, if Q is infinity, what you'll get back is a common notion of fairness called minimax fairness. So this has been looked at both in the federated setting and in general the fair ML literature through a notion commonly referred to as representation disparity. The idea is you want to minimize the worst performance on any one of the devices. Okay. What's nice though about this being a tunable framework and what we'll see in practice is that it allows you to trade off between whether you care more about, say, the average accuracy or this notion of fairness. And in particular, the way that we'll be quantifying fairness, both in theory and in practice for this objective, is in thinking about reducing the variance of the accuracy distribution. Okay, and just going back to the previous example, what you see is that if you take this objective and you run this on, for example, one of the benchmarks that I showed previously, you can do exactly this. You can perform just as well on average, but by avoiding these cases of sort of catastrophic failure. So intuitively, by using this QFFL framework, you're doing slightly worse on the best devices, but the benefit is that you get to avoid these really bad failure modes when you're training this model across a very diverse network. Okay. And this is a lot to take in one slide, but I just wanted to note that this kind of intuition from this kind of more toy example holds across all of the sort of benchmarks that we've looked at in practice. So to give you kind of one takeaway from these results, what we're able to show is that while doing just as well on average across these benchmarks, you can cut the variance of the accuracy distribution in half. So you can maintain that average performance, but you can prevent there being a lot of deviation in terms of how the model is performing across these heterogeneous networks. Okay, and I wanted to note here that we've also looked at some extensions to this work. And in particular, this notion that we looked at of fair resource allocation has also been looked at in other forums. For example, through something that's commonly known as tilting. Inspired by this, we've looked at this kind of more general modification to empirical risk minimization, where this objective when t is greater than 0 could be thought of as being very similar, kind of just a reparameterization of what I showed you on the previous slide. So you can think about this as trading off between the average performance or something like a min-max objective. But we also look, interestingly, at possibly making this parameter less than 0. And when this parameter is negative, what you can think about this as doing is actually kind of suppressing the outlier information, right? In QFFL, what we were doing was taking the devices with high losses, which you could think of as being outliers, and really amplifying, the performance on those devices. So having the model focus on those particular devices. Alternatively, it could be that those devices have high loss values because they're outliers or because they have corrupted data, and we may want to kind of suppress the model and suppress those outliers and ignore that information. Okay, I think that's kind of well highlighted actually in this plot here. So you can think at a high level about what this term objective is doing. As in the middle here, we have sort of the ERM objective. You're kind of just minimizing the average performance here, the average distance to any one of the points. When t is very small, when t is negative infinity, you're getting rid of all of the outlier information. And when t is very large, you can think about this as encoding a notion of fairness. So you want to minimize the largest distance to any one of these points. Okay, this is sort of out of the scope of federated learning, but I wanted to note that this work in federated learning has also kind of inspired some work more generally for problems in machine learning, and this is actually will be appearing next month at iClear. So I just wanted to point that out, and especially the connection to the FAIR federated learning work. Okay. So in terms of fairness, just to summarize some of the things that I just discussed, the motivation here is, after you've actually trained your objective, a natural question to ask is, how does the model perform across the network? And one issue that you can see in practice is that if you have heterogeneous data, it could be that the model performs well on average, but at the expense of the performance on some of the devices. So just training something like vanilla ERM may deliver poor quality of service in heterogeneous networks. And objectives like QFFL, or this more general term objective, can allow for a flexible trade-off between constraints like fairness or average accuracy. Okay, but this work in fairness, I think, kind of points out a much more fundamental question, which is, how should we really be modeling data that is diverse? Right, so the issue in some of the fairness work is that we're trying to train just this one model across the entire network, and it could be that the data differs a lot from the different devices. So we're asking this one model to perform very well, despite the fact that the individual devices might have very different looking data. Okay, and this kind of motivates why you might care about something like personalization for federated learning. Okay, in particular, kind of the fundamental question here is, how should we really be thinking about modeling federated data? On one extreme, if you had a network of devices, so here I'm showing each of these circles as being, say, a different device, and I'm drawing them to different scales to point out the fact that the data might be heterogeneous. So you might have data that looks different on some devices than other devices. So on one extreme, you can imagine the simplest thing to do, which would require no distributed optimization, would be to train completely separate local models, right? If the data differs very significantly across the devices, and if you have enough data for each of the devices, maybe it makes sense to just kind of train one model for each device. Okay, the obvious downside to this, and one of the reasons that we care about something like federated learning in practice, is that if you have a small amount of data on some of these devices, it could be that data from the other devices would be useful to help with the machine learning problem on a device that has an insufficient amount of data or insufficient quality of data. Okay, so you're really enabling the idea of personalization on this extreme, but you're not really allowing for any learning to happen between devices that may have similar data or be trying to solve similar problems. Okay, on the other extreme, sort of the de facto that we've been talking about for federated learning is that you train just a single model across all of the devices. So I'm calling this kind of the global approach. So even though all of these devices may have data that differs, maybe it doesn't differ very significantly, and so we can think about just training one model across all of the data. Okay, the downside here is that as we saw, I think with the work in fairness, it can be that when you have very diverse data, it's difficult for this one model to perform well across this entire network. Okay, and so what we were hoping to do in thinking about how to best model data is to potentially find something between these two extremes, right? So naturally, you want models to be personalized, but you also want to enable learning from peers in the network. And specifically, you want to learn from other devices that are similar to your own device, right? So you want to share information, but potentially in a smart way. Okay, and thinking about how to solve this problem, a really natural way to kind of satisfy these two constraints is through a framework known as multitask learning. And in multitask learning, the idea at a high level is that rather than just training one model for all of the devices in the network, you train a separate model, W sub T, for each of your devices or tasks. Okay, so this is the same objective from before. I'm just writing out the losses for a particular device T, but the main thing that's changed is now I'm allowing for each of the devices to have their own local or personalized model, W sub T. Okay, so what's interesting though in multitask learning is not only do you learn these personalized models for each of the devices, you also learn about the structure that exists between the different models. And the way that this is encoded in multitask learning, and this is a particular form of multitask learning, commonly referred to as multitask relationship learning, you learn not only these independent models, but also the relationships that exist between these models. And you can do that via this regularizer. So basically what this regularizer is doing is taking all of your models, putting them in this matrix W, and then via this task relationship matrix omega, it's learning some of the structure that exists between the models, which are just represented in this matrix. Okay, so this is a bit abstract here. So what exactly do I mean by this regularizer? What different things can this encode? Some examples might be that you could learn that all of the tasks are related, and what you're learning in this task relationship matrix is just the weights on the edges in this graph. So you're learning how related some tasks are to others. But you could also learn, more interesting structures. You might learn that there are outliers that exist in the network, or that there are clusters or groups that form between the different devices. Or potentially you could learn that there's some asymmetric relationships. So for example, one device is generating a lot of the most interesting information in the network. Now, you may notice this is actually work from a while ago. So this is a really expressive framework to think about how to possibly enable personalization in federated settings. One of the downsides, though, with some of the most commonly used objectives that kind of fit this high-level formulation is that they don't really scale well to networks with, say, thousands to millions of devices. And one of the reasons is that you have to learn this entire task relationship matrix across all of, say, your millions of devices. Often for many of these objectives, this would involve, say, inverting a million by million matrix, which can be quite difficult in practice. Okay, so with this in mind, in more recent work, we've actually formulated kind of a very simple form of multitask learning that has the benefit of being extremely scalable. Okay, and this simple form of multitask learning really considers just two tasks. The two tasks being the global task, which is a task that is just training the global model across all of the devices, the single model across all of the devices, and then a local task, which just considers the local data on any one of the devices. Right, so what you're seeing here is basically what we're training in this objective. What we're learning with this objective is we're taking a sum over our n devices. This would just be the losses, what we have from before, so the local loss on any device k. We're also learning these local models, W sub k. And this may remind you a little bit of what you saw with FedProx. What we're doing is we have this proximal term that limits any of the local models WK from deviating too much from the global model W star. There's two big differences here I want to point out with FedProx. So one is that in contrast to FedProx, this isn't just something that we're using to kind of robustify the global training procedure. We're actually learning separate models W sub K for each of the devices. And two, the model that we're trying to penalize here is the optimal model across all of the devices. Okay, so you can think about this as being a very simple form of multitask learning, where you're basically just trying to learn personalized models, but you're ensuring that they don't deviate too much from the global model. Okay, and you can think about solving this in an alternating fashion, where basically you can alternate between fitting the global model and then performing some local fine-tuning on your local model's WK. Okay, one thing that's nice about this framework, I just wanted to point out a few kind of practical benefits. Again, this is maybe kind of one of the most simplest forms of multitask learning you could think of, in that there's really just these two tasks that we're considering. And the only way we're kind of enforcing that there's a relationship between these tasks is by ensuring that these personalized models don't deviate too much in terms of the two norm from the global model. But a benefit of it is that if you think about training this in this alternating fashion, going between training the local models versus the global model, when you're training the global model, this is something that you can train using any of the previous works that have been developed to train a single model in the federated setting, right? So if you look here, if you're solving for W star, this just kind of results in you solving the previous objective that we have been talking about. So this preserves all of the same sort of privacy and communication efficiency that you typically have in the federated setting when you're thinking about just training one global model. Okay, so you can think about this as just being kind of this additional personalization add-on on top of these global solvers. Okay, what's interesting though, and what we've been noting in some recent work, is that there are some really big benefits to using even this very simple form of multitask learning. So one of the known benefits, and this is something that's been observed in prior work in multitask learning as well, is that there are accuracy benefits for using these personalized objectives, right? Especially when you have these heterogeneous networks where the data might be differing across the devices, it makes sense to learn these personalized models. Okay, and you can see this in terms of, say, looking at the test accuracy across some common benchmarks. Multitask learning can improve upon these two extremes we talked about previously, learning just completely local models or completely global models. Okay, but in fact, there are some other benefits of using personalization. So one of them relates to the previous segment of the talk where we were talking about fairness, right? So in the fairness work that we were talking about previously, we were trying to train one global model and ensure that that model was fair to all of the devices in the network. One benefit, which I think is quite intuitive, of personalization is that it can enable more fair performance. We can reduce the variance of the accuracy distribution by learning these personalized models. Okay, but what's really interesting, I think, with this, even with this simple form of multitask learning, is that there can also be robustness benefits. So specifically what I mean is that if you have a situation where you have, a network of devices and some of those devices are either just, corrupted, or there's some failure on the device, or some noise in the data, or potentially there's an attack, just by learning personalized models, by not relying on one global model, but by learning models that differ across the network, you can have some form of robustness built in, right? So you can learn models that are kind of separate for the corrupted or different looking data in the network, and that helps to preserve some of the performance on the other devices that are, have clean data and have not been corrupted. Okay, and this was kind of something surprising in terms of this work, is seeing how effective this actually was in practice, especially related to things like, common methods that have been developed to provide robustness when training a single global model. So what I'm showing here is looking at the performance, the test accuracy, the average test accuracy across the clean devices, when training this multitask learning objective, this DitTo objective that I talked about in the previous slide, versus training a global model and applying to that something like multi-crom. So this is a common method that's used to enable robust performance. So you can see we're getting this big benefit just from using multitask learning alone. Okay, there's one last thing I wanted to kind of point out on this slide, which is that personalization can be especially effective when you care about all of these things simultaneously, right? Often we don't just care about accuracy or just about robustness or just about fairness. We care about all of these things at once. And one kind of potential issue with some of the current work is, think about the FAIR objectives that we talked about. We talked about, say, training a mini-max objective, so minimizing the worst performance on any one of the devices. If one of those devices is corrupted, you can easily, potentially overfit to that one device, right? And you can see that with this, for example, the performance of this FAIR objective, where we're looking at this kind of mini-max performance, right? You can see that it starts to really degrade in performance because it's overfitting to these corrupted or malicious devices. Similarly, if you think about some of the work in robustness, say, let's look at a simple example like taking a median as an aggregation approach. Intuitively, if you're looking at the median, that can really help to get rid of the tail behavior. This is a nice thing to do if that tail behavior includes some corrupted data. But if it includes data that's just different from the other data because our network is heterogeneous, then we might be getting rid of important information. And so you can see on the right here that you can have issues where some of these robust baselines really increase the variance and the accuracy distribution. Okay, so kind of just summarizing the takeaways here. I think modeling is an incredibly important problem when we're thinking about how to actually solve these federated learning problems. And thinking about how to correctly model the data can provide benefits, not just in terms of accuracy, which is what we normally think about, but also in terms of these other constraints that we've talked about, like robustness and fairness, which are common things to think about in these federated networks. Okay, this is just kind of showing across both of these axes of looking at accuracy and fairness that this particular objective, DitTo, kind of can achieve both of these things simultaneously, which again is, I think in practice, you don't care just about one of these constraints at once. You often care about both, all of them simultaneously. Okay, so just to summarize here in terms of this last point, what I wanted to point out here is that modeling is really, in some sense, the most fundamental problem, right? What is the actual objective that we should be solving? And then we should think about, okay, how should we solve that objective? The thing I wanted to point out here in terms of personalization is that multitask learning is a really nice principled way to think about performing personalization. And there can be benefits not only in terms of accuracy, but in terms of these other sorts of constraints like robustness and fairness for correctly modeling this heterogeneous data. Okay, so I wanted to leave just the last couple of minutes to talk about some more forward-looking directions. So what's next? One kind of underlying thing that I've been talking about today is the importance of heterogeneity. So how that might affect our optimization methods in federated settings, how it affects the evaluation of the models that we're learning, and how it affects the models that we should choose to fit to our data. But really critical to understanding how prevalent this issue of heterogeneity is understanding what heterogeneity looks like in real federated networks, right? And we have some sense of this via current benchmarks and things like LEAF, which I've helped to develop with a lot of fantastic collaborators. But we need to go further, right? So I think there's really a need for more open source data sets from folks who are using federated learning in practice. In addition to these data sets, we also need practical diagnostics for determining what heterogeneity looks like and how we can best adapt to that heterogeneity. So this is something that really motivates me, and I'm excited about this particular direction. So if you potentially be interested in collaborating along this line, please let me know. Okay, and lastly, I wanted to end here on maybe more of a positive note. So we've talked about a lot of potential dangers or challenges with thinking about how to handle statistically heterogeneous data. In terms of the optimization methods we're running, in terms of enabling fair performance, and in terms of modeling our data. But I wanted to end with kind of positing that there may also be some benefits of heterogeneity, especially if we understand what this heterogeneity looks like and we can leverage it. Okay, and one example where we've been able to show this is through a problem in federated clustering. And in particular, what we do, and this relates to kind of the overarching goal here of communication efficiency, is we develop a one-shot clustering technique, which is termed K-Fed. So basically what you can think about is just solving a k-means problem locally on the local data from any one of the devices, and then sending those cluster means back to a central server where they are then aggregated. So this is a one-shot clustering technique. It only involves one round of communication from the devices to the central server. And I think kind of intuitively for this problem of clustering, where what you're trying to do is to learn about kind of the different clusters or structure that exists in the data across the network, it may be intuitive that something like heterogeneity can actually be beneficial here, right? But what we were able to show is theoretically that heterogeneity can actually lead to provably stronger guarantees in terms of your clustering behavior. Okay, and this can enable a variety of applications. So in particular, we've looked at some applications in client sampling. So clustering can be useful to determine, what clients or devices you should sample at every communication round in order to potentially speed up your convergence behavior. It can also be useful from a modeling perspective. So if you understand, say, different clusters that exist between the devices, you might learn, models that are specific to a specific cluster in the network. Okay. But the kind of key punchline here is that if you're thinking about this one-shot clustering technique, what you can show is that if you compare the performance of this one-shot clustering in terms of kind of, this is the k-means objective, basically what we're plotting here on the y-axis, and you want this number to be lower. And what you can show in practice is that if you compare the performance of something like this one-shot clustering approach on a heterogeneous network versus a network where all of the data is IID sampled across all of the devices, you can really have a much better performance by using just this one-shot clustering technique than if you were in a completely IID setting. Okay, so this work is some initial work, and the goal here is really to think specifically about how heterogeneity may also be beneficial for federated learning. So some of the things I've talked about today, you could view as being potential negatives of heterogeneity, slowing down our convergence, making it more difficult to enable fair performance or accurate behavior. But this is one scenario where we've been able to show that heterogeneity can in fact be beneficial in the sense that allows this simple one-shot clustering technique to actually really perform much better than other baselines if you were just looking at IID data. Okay, so thanks. I don't know if we have time for questions, but I'd be more than happy to answer questions if anyone has one.
There are some questions in the chat, I think.
Okay.
Or at least one question.
Yeah, the question is, how would you analyze convergence of DitTo if the cost functions are non-convex? Because even in the constraint, there would be non-convexity. So one thing I wanted to point out with this, with this DitTo objective, I'll just go back to this slide, is that this is pretty modular. So the way that we're formulating this is that we're alternating between solving the global model and then the local models. So when you're solving the global model, you can just kind of plug in any sort of convergence analysis you might have, even over non-convex objectives, to figure out the convergence rate for this global objective. So the main question is, how does the convergence of the local model proceed? And when you're training the local model, importantly, this global model is fixed. So again, this is something where you can kind of plug in, assuming you understand how these relate to one another, you can kind of just plug in kind of previous results for analysis on just, and this is actually in some sense a much simpler problem because you're just looking at the behavior on a single device. So I don't know if that answers your question, but if you're interested in looking at the particular convergence guarantees that we can show, I would encourage you to look at our paper where we provide some more of the details. But that's the intuition, is that you're thinking separately about how to train the global model and the local model. And because we're solving these in an alternating fashion, you can think about just decoupling the convergence of both of those.
Okay. There are one or two more questions.
Yeah, there was a question about, have you investigated other metrics of fairness things like demographic parity? That's a really great question. So we've looked at this one particular notion of fairness, and I think there's a lot of work to be done to think about potentially some of these other notions of fairness and how they might be affected in the federated setting. This one on looking at the variance of the accuracy distribution, I think is very natural when you know that the data might be very heterogeneous. But I think it's also really important to think about how other metrics might be impacted by the federated setting as well. So I think that would be a very interesting direction of future work, but we have not looked at that directly. Oh, here's another question. Yeah, this is great. So how do you have any advice on how to set the hyperparameters in practice for things, for example, like Q, fair, federated learning that we've talked about? So I have a couple answers to that. So one of them is that I think one of the goals of our work is to show how the objective, both in theory and in practice, varies depending on how you set this hyperparameter. So kind of one of the goals of the theory that we've developed is to help provide some guidance for how to set this. But generally, I think this is something where there has to be a little bit of a human in the loop here in terms of at least guiding how much emphasis you want to put on fairness versus accuracy, right? So the benefit of having this hyperparameter is that you can tune that, but it still begs the question of, there needs to be someone guiding the objective to say, for this particular application, I really care a lot more about fairness than average accuracy. But given that, given that you have that constraint, then you can incorporate that in the QFFL objective. So, for the constraint that we had, for the results that we showed, we wanted to have the same average accuracy, but reduce the accuracy distribution. So that can be done just by looking at the performance on some validation data, just like you would with any kind of typical hyperparameter tuning. And I think we looked at kind of a few hyperparameters. So you can I think we have all of the details in the paper if you'd like to see more information there. But yeah, that's a really great question. That's the downside of potentially introducing a hyperparameter, then you have to set it. Okay. There was a question on, are the weights for each device in QFFL assumed to be known? And if so, would optimizing over those weights PK make the system fair? So this is a really good point. So we kind of generally wrote this objective out via this P sub K term, so that this could encompass this idea that exactly you might want to reweight these losses depending maybe on some prior information that you have. For many objectives, you would think about this as just being a 1 over n. So you're typically just thinking about taking the average. The one issue, I guess there's a couple issues with assuming this is known. So we assume that this is fixed beforehand. And the reason that we do is that the way that we're enforcing fairness is by kind of amplifying these losses by this exponent. That's what we did with the QFFL work. The benefit of that is that this is you can think about this as being dynamic, right? The issue with having fixed PK fixed is that you need to know how you want that PK to be set before you even start training your model. So if you wanted to set PK beforehand, you'd have to have some information about, I think this one device is the device I really want to make sure that my model fits to. Instead, what kind of adding the fairness component to the loss does is it allows you to dynamically adapt to the fact that some of the losses might become higher, larger or smaller throughout the training procedure, depending on how the model is affected. So that's the benefit of incorporating it in terms of the loss component. I'm not sure if that answers your question.
Thanks, Virginia, for a great talk. Let's give a round of applause to Virginia.